Okay, let's get started. Again, we're looking for a new faculty member in the department in data science and machine learning. And we have the third of our four candidates visiting today. Dr. Berger is visiting from University of Arizona. He's going to be talking about machine learning enhanced visualization. So just to put this into context, about 10 years ago, the big data revolution started. 5 years ago, the deep learning revolution started, the AI revolution started. Giving all this data, we started to be able to produce neural networks that could find patterns in these very large data sets that we now have and could make accurate predictions based on what those models had learned. We are now struggling with trying to understand why these neural networks are able to predict the way that they do. Can they explain to us why they're making a given prediction? If we want to make machines that are smart and accurate and predictive, we would also like them to be safe, and there's lots of definitions of that. One of them is that we want them to be able to explain their reasoning to us. One component of that is visualization. How can we actually visualize what a machine learning algorithm is doing or how it's predicting? And Dr. Berger is going to be talking about that today at 1:15 on the fourth floor of the Davis Center. Come and find out a little bit more about that, and also come and get your caffeine and sugar fix in the afternoon if you should need it. Okay. All right, so jumping back to the schedule, where we are and where we're going. Last Thursday we finished Lecture 6, which concludes the second of our 6 themes, in this case the tools of the trade. So again, we've done this sort of very shallow treatment of all of the major moving parts of an evolutionary robotics experiment, and in the assignments you're working your way through some of those moving parts. And we're going to move on today to theme number 3, where we're going to look at some of the very first experiments in evolutionary robotics. As I mentioned, this is a pretty young field, so we're going all the way back to the early 90s, and we're going to look at a few. In Lecture 7, we're going to look at the first 2 experiments that took place in Europe. Before we do, a little bit about the assignments. I've got some more emails from people that are struggling with their USB drives. Again, I apologize. I don't know if it's because we bought the cheapest brand of USB drives that are out there, or if it's the way we flash the Linux operating system onto the USB drives. So again, my apologies for those of you that are struggling with that issue. If you are, let us know. We can try and swap it out. If that's not working, again, we're happy to give you an extension on your current assignment. Some of you have switched over from using the USB drive to a dual boot partition on your computer. Again, for our purposes, whatever works. If you have to switch tactics, just let us know, and I'm pretty sure we can accommodate you. So speaking about the wonkiness of the USB drives, remember, regardless of what solution you're using, back up all your code, right? You're building all these assignments on the back of the code you developed from the previous week, so make sure you have that saved somewhere. Okay, so undergraduates, you're moving on to assignment 4 today, which is neurons and synapses. So you've now gone through objects, joints, sensors, so you now have a robot, hopefully that exists in your physics engine, but it is maximally dumb because it cannot react to what it senses. So it can see the world around it, but it can't do anything about it. So we are now going to connect up the sensors to the motors with neurons and synapses so that at a given time step in the physical simulator, sensor values arrive at the sensors and they then flow along the neurons and synapses to the motor neurons. And the particular transformation from sensation to action is going to be influenced by what aspects of the neurons and synapses. Aside from putting neurons and synapses into your system, what else are you going to have to set? The weights of the synapses, right? The weight of influence of a synapse, which is going to dictate the weight of influence of the presynaptic neuron, the neuron that sits at the base of the arrow, to its influence on the postsynaptic neuron, which is the neuron that sits at the head of the arrow, which represents the synapse. In PyroSim, you do not have to set the activation function, that's set for you. So when you're setting a neural network, we need to set the neurons and synapses, set weights for the synapses, and activation functions for the neurons. That's done for you. So you're just going to be setting, when you get to the synapse the synapse project here, you're going to be setting synaptic weights. Okay, so at the end of assignment 4, as you're going to see, you're now going to have a robot that's jumping around randomly in the physics engine, because we're going to have random synaptic weights, which means there's going to be a random transformation of whatever the robot senses at a given time step, and the commands that are set to the motors. You can imagine what you're going to then be doing in assignment 5 and 6 and so on, which is tuning the synaptic weights to get your robot to do whatever it is you want your robot to do. Sound good? Okay. Some of you have been working ahead and sending back slight errors in the instructions as you go. Thank you very much for that. One of them that someone pointed out is in the neurons assignment. I'm pointing you to our engineering drawing here, and there was an error before SN1. T0 pointed to SN1, and T1 pointed to SN0, which was wrong. I fixed it. It should be, as you would imagine, we're going to have the 0th sensor neuron associated with the 0th sensor, and so on. Okay. Just a minor thing, but just in case you came across that. Graduate students, you're going to start in on assignments 7 and 8, and I will put them up on Blackboard when I get back to my office. Any questions about the assignments? So far, so good? Okay, so let's start in on our history of evolutionary robotics. Before we do, just to talk about this theme as a whole, talk about the first experiments, and then we're going to look at a set of 5 lectures, 3 of them around this idea of minimal cognition. So after evolutionary robotics began in the early 1990s, it kind of branched in 2 different directions. We're going to look at those 2 different directions. One direction said, what is the simplest possible robot that we can make in the simplest environment with the simplest fitness function and the simplest behavior? So make it as simple as possible that if we evolve these minimally cognitive agents, someone else who has no idea what evolutionary robotics is but looks at the robot will point at the robot and say, that's the beginning of cognition. That's the beginning of intelligence. I can see that the robot is making decisions. It's starting to plan ahead. It's deciding which of 2 objects it should go after. This particular set of experiments we're going to look at here, as you can probably imagine, was inspired by Bradenberg's vehicles, right? Keep things very simple, but even if we keep things simple, we can get surprisingly interesting behavior. That's one branch that we're going to look at. The week after, we're going to look at locomotion. So one of the big challenges in autonomous robotics that sets autonomous robots apart from laptops and cell phones and embedded devices and all the other technology we've developed is that a robot has to get itself from point A to point B in a world in which there are people and objects and weather and all sorts of things going on. So one of the biggest challenges in robotics is locomotion, and particularly legged locomotion. So we're going to look at some of the early experiments in that area. Okay. Before we get to that, first years of evolutionary robotics. The field started in Europe. So we're going to look at the Italian approach today, and then the English approach in about 45 minutes from now. The Italian approach was carried out by 2 Italian researchers in Switzerland. Just a little bit of geography for you. Okay. And they were working actually back in the early 1990s with these little small hockey puck type robots called the Kepler robots. They're surprisingly long-lived robots. There was a product video from 2013. I think they're still on the market today. They're a nice little simple robot that's been around for a long time. Why would they start with physical robots, given the fact that physical technology back in the early 90s was probably primitive compared to robotic technology today? Why didn't they start with physics engines? So much easier.
They didn't have powerful physics engines.
They didn't have powerful physics engines. They didn't have physics engines full stop. The first one was sort of introduced for general use in 2000. So the field started really before at least physical simulation was possible. So 2 very brave researchers said, let's try and evolve behaviors for physical robots. Nice thing about the Kepler, obviously, is it's small, so they could carry out tabletop experiments. You didn't need a very large area to test out large robots. And the Kepler was built with this modular architecture. So very, very simple design here. We've got 2 wheels, so very much like a Bratenberg vehicle. And then you could stack little add-on modules on top. In the upper right photo there, you can see a little gripper, which has gripped a little sugar cube and then lifted the object. You might remember a simulation like that from the very beginning of the semester. Simple solution for object manipulation. You can also, instead of the gripper, you can put on a very simple visual module. So there was a little simple camera they would put on, and this camera would give back linear vision. So what's linear vision? Basically, you can imagine that this camera is looking with a 36-degree field of view, so about this, just in front of it. And it gets back 64 numbers between 0 and 1, where a lower number represents lower light levels and a higher number represents higher light levels. Here's what the little Kepler is seeing at this point in time. What is it seeing? Hard to say, right? It doesn't have that great vision, but what's the situation here probably?
Is it seeing the block that it's trying to pick up?
There's a little obstacle in front of it. Who knows what it is? Maybe it is the little sugar cube, but it's something that's 36 degrees, so whatever that is, something that's obstructing about 5 degrees of its vision right in front of itself, right? So it can't see much, but it's enough for certain things. For some of the behaviors we're going to evolve. Okay, pretty simple creature, but good for getting started. Okay, so what did they actually do with this robot? Well, they conducted arguably the first evolutionary robotics experiment. So they put the little Kepler on a table, and then they attached the robot with this tether back to the computer. So the computer is going to do all the evolutionary algorithm, and the robot is going to do the behaving. So the computer is going to send what to the robot, and what is the robot going to send back to the computer? What information do these two devices need to communicate?
The robot maybe would say, like, it would be giving sensory information of what it sees, and then the computer would be telling the robot what to do based on that information.
That's it. So the robot sends back sensation, and the computer sends back what the robot should do next. What is the computer using to tell the robot what to do next? It's getting sensory information in and sending motor commands out to the robot.
Updated weights? Were they using neural network?
They were using a neural network, so the neural network is actually running on the computer, right? So the brain of the robot is not even on the robot, it's in the computer, right? And we've got the neural network in the computer, and we have the evolutionary algorithm, which is tuning the weights, right? Searching through the space of all possible neural networks with different synaptic weights, trying out each neural network on the robot and seeing how well it does. And how do we know how well the robot does? Well, we get sensory information back from the robot and compute some fitness function. As you're going to see when you start doing evolutionary algorithms with PyroSim, you're doing something similar, except you're going to send your neural network across to the simulator. Neural network will run there and send sensory information back for your code to compute the fitness of that neural network. Okay. So how did they do this? How did they get the sensory information to the robot? Well, they had a little laser turret up in the upper right corner here, and the robot could sense that laser, and the robot could use that to figure out its current position on the table, X, Y, and its current heading. So instead of having all the sensors right on the robot, they were kind of cheating a little bit and putting in a little bit of infrastructure around the robot so it could figure out X, Y, and heading. Let's assume the robot sends back X, Y, and alpha, or the heading, as it's moving about on the table. What kinds of fitness functions could you create for this robot? What might you try and evolve it to do? The fitness function is going to take all this sensory information and compute a single number, which is how good or how poorly the robot did at something you want it to do. What are some of the things you might try and get it to do?
Object avoidance.
Object avoidance, right? So we could put some objects on the tabletop and ensure that the robot doesn't bump into them. Super simple way to solve that problem. If you're the robot and you're not supposed to bump into any obstacles, don't move, right? As you'll see as we go, evolution is always smarter than you are. Whatever you think you want, which is really avoid obstacles while moving, which is probably what you meant, right? If we don't put that in the fitness function, evolution will say, sure, there's an easy way to solve this. Okay. I'll bet you they tried that and said, okay, that's not quite interesting. Let's make this a little more interesting. So they made a little racetrack out of these little blocks on the table to make a little simple track or a simple maze. And they're going to try and evolve a robot that will race around the maze as quickly as possible without bumping into obstacles, right? Don't hit the wall. Okay, so as I mentioned, they had this laser turret which is going to allow the robot to figure out X, Y, and alpha, but the robot itself also had 8 sensors on board. It had 6 proximity sensors in the front. So each proximity sensor returns a value, which is 0 if there's nothing in front of the robot, or at least there's nothing for at least 5 centimeters in front of the robot, and that value will climb from 0 up to 1, and at the limit, at 1, the proximity sensor is touching an object. So the higher the proximity sensor value, the closer the object is.
Is that neural network architecture in the robot as in addition to whatever is being simulated in the computer, or is the proximity data being fed back to the computer?
It's all being fed back to the computer. So we're drawing the neural network in the robot, but it's being run inside the computer, right? Remember, the neural network transforms sensor values into motor values. Doesn't really matter from the robot's point of view where that neural network is. Okay. We have the 2 wheels, so we're going to send 2 commands to the 2 wheels, negative and positive numbers. We're going to squash the range of the motor values. Remember our activation function. So in this case, they squashed it to between minus 0.5 and plus 0.5. Minus 0.5 is the wheels spin backwards as quickly as possible. 0 is the wheels don't turn. Plus 5 is they spin forward as quickly as possible. We also have 2 proximity sensors on the back of the robot. So we have 8 sensors, 2 motors. And they're all connected up as follows. So this is drawn a little bit differently than some of the neural networks you've seen before, but you should be able, through visual inspection, to see that all of the 8 sensors have synapses connecting them to the motors. Right? Each of the 8 sensors has 2 outgoing synapses that connect to the 2 motor neurons here. And those 2 motor neurons, little pluses, remember they sum all of the incoming values from the presynaptic neurons. They sum it, squash it through an activation function, and push those values out to the wheels. These values, minus 0.5 and plus 0.5, are desired angular velocities. So we're dealing with wheels here, which means this robot is controlled by velocity control. We're going to treat the values that arrive at the motor neurons as desired velocities or angular rotation. Right? In the code you're developing, the commands that are arriving at the motor neurons when you put them in this week, this is position control. In position control, you treat the values that arrive at the motor neuron as desired position, or in our case, desired angles. Right? So position control and velocity control. Basically, when we're dealing with a legged robot, it's position control. We're dictating the desired angle of the joints. When we're dealing with wheels, it's velocity control. What is the desired angular velocity of the wheels at any given point in time? Okay, we'll see experiments that sort of mix and match these things. Okay, so the experimenters connected the 8 sensors to the 2 motors. They also set whether each of these 8 times 2 or 16 synapses, they set whether they were excitatory or inhibitory. They're going to allow evolution to evolve the weights themselves, the magnitude of the weight of influence, but they're going to set them to be excitatory or inhibitory. So they're going to sort of restrict the range of weight values for these given synapses. What can you tell me about the pattern of excitatory and inhibitory connections? There is a pattern there that the investigators built in. It's not arbitrary. Which ones are the excitatory ones and which ones are the inhibitory ones? How are they distributing them throughout the robot? Yep.
The inhibitory ones are actually on the opposite side.
Exactly, right? So remember when we talked about Bradenberg views, these are contralateral connections going across the line, right? So you're right, the inhibitory connections are contralateral. What about the excitatory ones?
They're attached to the same side?
They're on the same side, right? So that's ipsilateral. So we have ipsilateral excitatory connections and contralateral inhibitory connections. So now let's think about the weights themselves. What does that mean? If we're restricting a synapse to be inhibitory, what are the valid weights for that synapse? We haven't set the weight yet. We're just saying whether it's excitatory or inhibitory.
Negative.
Exactly, right? So we're going to restrict, in the inhibitory ones, the weights are restricted to be negative numbers. In the excitatory connections, weights are restricted to be positive values. Why did the investigators make these restrictions up front?
So it'll turn away from obstacles.
Exactly, right? Remember your Bradenberg vehicles, right? So this is the coward, right? So generally speaking, it's going to turn away from obstacles. So they're kind of cheating a little bit by sort of biasing search evolution to say you can't search the entire fitness landscape. We're going to restrict you to the coward part of the landscape, right? You can search over all possible cowards, just basically stay away from the obstacles. Okay, so they're restricting things a little bit. As we move forward from this very first experiment all the way up to the present day, one pattern you're going to see across all of these experiments is we're going to make less and less and less assumptions about the robot itself, right? This is sort of the most extreme example. We built the robot, 2 wheels, 8 sensors. We're going to assume every sensor is connected to every neuron, every motor. We're going to restrict excitatory and inhibitory, and just the remaining piece, the small sets of weights, evolution, you can work on that part. Okay. Okay, so now let's do a little bit of the fun part. Now you know what the robot can sense. At every point in time, it's going to get back 8 numbers, which are these proximity sensors. And let's also assume that the robot, the robot can sense 8 numbers. But the computer, which is collecting all the information and is going to compute the fitness of a given neural network, the computer has access to 10 numbers, the 8 sensor values plus the speed of the left and the right wheel, VL and VR, which correspond to this over here. Okay, now we want to make a fitness function here, phi, which is going to reward robots that travel quickly around and around the racetrack, and 0 if they don't. Sorry, 1 if they travel maximally quickly around and around the racetrack, 0 if they don't. How do we construct that fitness function given these 10 variables? Let's start with obstacle avoidance. We've made the robot a coward by making these excitatory and inhibitory connections, but we're also going to try and get our robot to move. So if it's moving very quickly and it still is trying to move away from the obstacles, it may not be lucky, right? It might be traveling too quickly to do that. So we're going to add in a term to this fitness function, something that in addition to forcing it to be a coward, we're going to penalize the robot if it gets too close to the sides of the racetrack. What is that term going to look like?
Well, if you want to minimize the sum of the closenesses, the proximity, you want it to go fast but not too fast.
Okay, so we could minimize the sum of these 8 numbers. Okay, so remember that, right, we want to minimize the sum, right? So lower is better, so we could try and minimize the sum. We could take the sum and ask evolution to try and make that sum as small as possible. That might help with obstacle avoidance. And again, the robot's going to be able to solve that no problem, just doesn't move, right? So it's not enough to just penalize proximity sensors. We're going to have to also reward something else.
We divide by the speed.
You could divide by the speed. And what's the speed here? We have to ultimately ground this in these 10 variables.
VL plus VR.
VL plus VR, okay, we could do that. Other ideas? Is that going to do it?
We could continually ramp up the motors VL, VR while making sure that the robot turns away from the sort of, if the first half of the array is activated,
Yep.
turn away from that. The right half of the array, meaning sort of like 4 through 7 or 4 through 8, turn away from that direction.
Okay, that sounds good. We could try that. So what we're doing now is constructing a fitness function to try and reward for what we want and penalize for what we don't want. There's lots of different solutions that might work. The investigators themselves came up with this function, which is the product of 3 terms here. And we're going to walk our way through these 3 terms. The first one, uppercase V, is the most obvious one, right? The robot can't stay still. We want it to move. But they didn't just take the sum of VL and VR. They took the sum of the absolute values of VL and VR. Seems kind of odd. Why take the sum of the absolute values of these two?
Because moving backwards is still moving.
Moving backwards is still moving. So if we sum them, we're explicitly rewarding for forward travel. And in the spirit of evolutionary robotics, we want to try and allow evolution to explore all the options. So if moving backwards quickly through the maze makes sense, that's fine, right? Seems anti-intuitive to us. We don't want a human driver in a car driving as quickly as possible backwards. Feels uncomfortable to us. But remember the Libet experiment on free will, right? Thinking about thinking is misleading. Just because it feels like not the right solution to us, we don't want to cut that solution off from evolution. So, absolute VL plus absolute VR. If evolution wants the robot to travel forward, fine. If we want it to travel back, that's also fine. Let's look at the third term now, because this one's a little bit easier. They're taking 1 minus the maximum, or we could have taken the minimum. That works fine. So at any point in time, I is going to represent the value of the greatest of all the 8 proximity sensors, right? If you're about to crash into an object, the only thing you care about is the proximity sensor that is maximally stimulated, right? So we're going to take the max of that, and we're going to penalize the robot, 1 minus. As it's spinning around and around the maze, if it's going really fast and gets close to an obstacle but doesn't hit it, then one of those 8 values is going to spike. It's going to go very high. It's going to approach 1, and suddenly that third term is going to plummet towards 0. And 0 times anything else is close to 0. So by multiplying these 3 terms together, the investigators are saying, robot, if you are ever flying around the maze and you get very close to an object, I don't care how fast you're going, you're not going to get a reward for V at that time step. Right? So V could be very high, it could be moving very quickly, but if it gets close to an object, that cancels out the reward it would have got in uppercase V. That's why they're multiplying the 3 terms together. Okay, let's have a look at the middle term. Why do we need this middle term if we're selecting for velocity and minimizing, we're minimizing object collision? Yes?
If the values are too large, they're too different, then it would just be spinning like a circle.
Absolutely, if they're too different, right? So if we had just summed things in V, we wouldn't have that problem, right? So if we just said VL plus VR, forget the absolute, we're selecting for forward travel, and as long as we avoid collisions, we're probably good. But they didn't want to restrict the robot to just forward travel. They wanted forward and back, so they said absolute. And then evolution, I'll bet you the experimenters originally had just the first and the third term. And evolution is smarter than all of us. So evolution said, great, yeah, I can maximize V, no problem. Spin around in place as quickly as possible. I don't get close to any obstacles. We're all good, right? So now we have robot, with uppercase V, you're allowed to go forward or back, but do it as quickly as possible. Third term, avoid obstacles. Middle term, don't cheat by spinning in place. The reason we're spending so much time on this fitness function is that one of the things that's tricky about evolutionary robotics is specifying a good fitness function. I told you this joke already, but evolved robots are like teenagers. They'll often do exactly what you ask them to do in the fitness function, but not in the way you wanted them to do it. So you often have to go back and forth a few times between creating a fitness function, doing some evolution, seeing that evolution is smarter than you and came up with a perverse instantiation of what you wanted, right? Go back, make some changes to the fitness function, back and forth, back and forth. I promise you, whatever you decide to do in your final project, you'll end up doing this. Okay. Okay. Turns out that at least with those three terms multiplied, it actually works. So this is a picture we're going to see many, many times in this class. This is a fitness curve plot. So on the horizontal axis here, we have the number of generations. So with the Kepler robot, they performed 100 generations, which took with the physical robot 66 hours or almost 3 days. I hope they didn't do this all in one shot. One generation took about 40 minutes. The upper plot, the upper curve there, and the vertical axis is showing the fitness according to phi here, right? Okay. So the upper curve, which it's hard to see in this picture, says max, and the lower curve is average. The upper curve is showing the best robot in the population at that time. Remember, they're evolving populations of neural networks. So at every generation, they evaluate every neural network. They get a fitness value for every neural network, and the neural network that got the highest fitness value, that's that point. They then averaged all the fitness values within the population, and that produces the average curve. So we can see in the upper curve that the best robot, the best neural network in the population is increasing in fitness, and the population as a whole is becoming more fit. Yes?
How many robots did they have to try? Like, how many were in one generation?
That's a good question. It doesn't say here on the slides, and I don't remember if they said in the paper. It might be in your readings for the day. You can go back and have a look. Yes?
Out of curiosity, how did the velocity, or how did its lap time compare to just kind of hard coding, go here, go here, go here? As sort of
It was,
benchmark?
so how well does it do to what a human could do? So if you sat down, if I gave you the Kepler and said, program the Kepler to drive around in the maze, you might do what you said, right? Go and then turn and go fast, turn.
Yeah,
Okay.
I'm just curious how it.
It's hard to say because, again, not all the details were reported in this experiment, but I'm pretty sure that you could have programmed it to go faster. And it goes slower for an interesting reason, which we'll come back to on the next slide. Okay, so here's another picture that, again, I'm including just to sort of give you ideas for your final project. So one of the things you're going to have to do in your final project is show all of us how well did your evolved robot do, and there's lots of different ways of visualizing that. This is a nice one because you don't get a feel for absolute speed. You can't tell from this picture how fast the robot was actually going, but you can sort of get a feel for change in acceleration, speeding up and slowing down. How can you see that in this visualization? That's Rachel.
Overlapping lines.
Sorry?
Overlapping lines versus far apart lines.
Exactly. So here it is, slowing down, and then speeding up. So each line represents a constant unit of time period, right? Okay. So you can sort of see speeding up, slowing down, and something about the strategy of this robot. What is its strategy? It's not doing what you said, right? Going straight, stopping, turning, and then going.
It's trying to be continuous.
It's more or less continuous, right? So it's somewhere in between. right? The optimal solution, as you could have probably imagined, is to describe as smooth a curve as possible in this restricted space. Didn't quite do that, but pretty close. This is another fitness plot taken from exactly the same run, but now they took those three fitness components, overall velocity, proximity to obstacles, and differential in the wheel, so the amount of turning basically that happened. If you look at the solid line, this corresponds to the velocity of the best neural network in the population. Not surprisingly, it goes up. So the first robot was moving relatively slowly, and it got faster and faster and faster over evolutionary time. What about the dashed line here, 1 minus I? What's happening there?
Keeps getting really close to walls, so the relative importance of wall avoidance seems to be getting more important, right?
Becoming more important, that's right. So if you look carefully, and again, I apologize, it's hard to see in this figure, the dashed line actually starts up here, right? So it's actually doing pretty well for this term. Of course it's doing well because it's going very slowly. It's probably barely not moving at all, so it's staying away from the walls. But as the robots start to evolve to get faster, even though they're cowards, by definition, they're going to start getting closer to some of the walls in the maze. So this term is actually coming down a little bit, right? The third one, differential drive, it's kind of hard to see. It's kind of bouncing around. What this plot is showing you is that evolution is trying to strike a balance between these three things that the investigators asked it to do. The investigators multiplied all these three terms together, so they're telling evolution you have to maximize all three, which is a bit of a tricky thing, right? Evolution has to strike a trade-off. It could go faster, but if it goes really fast, it might be inevitable. It might be hard to avoid the obstacles, right? So it's not just a simple matter of evolution improving all three at once. It's trying to find a path through the space of all possible neural networks to gradually bring all three lines up as high as possible. Again, when you get to the final project, you might also have to create a fitness function that says, robot, I want you to do this, but not in this way, and as quickly as possible, and as energy efficiently as possible. And evolution is also going to have to try and strike a balance between these antagonistic terms as possible. This is just, I put this up here, it's kind of an interesting plot. They tried to show this in 3 dimensions. So we have 3 fitness terms. So we have v 1 minus I and the square root term up there. I'm sorry, I forgot to talk about the square root term. Why is it 1 minus square root of delta v? Why not 1 minus delta v? What does the square root function look like if you plot it? Grows very quickly, right? And then starts to slow down. So what that means, if you wrap a term in your fitness function into square root function, that means anytime you make a slight improvement in that term, which in this case is delta v, which in this case, if you make an improvement in delta v, that means you align the speed of the wheels better, you get a big fitness bump, right? Later on, if you already have a good delta v and you make a bit more of an improvement to delta v, you're at the shallower part of the curve of the square root curve. You get less of an improvement. There's a diminishing returns here. So by wrapping that term in a square root function, they're telling evolution, make rapid improvement in the differential, and then we don't care so much later on. Why are they telling it to not care that much later on in the differential? Why are they not giving as much fitness for aligning the speed of the wheels?
Maybe once it gets past the first part of the curve, it's good enough, and they want to put more emphasis on the other 2 variables.
Exactly, right? Put emphasis on the other things. Don't spend too much getting really good at delta v and maybe v, because you can't turn, right? You've got to reduce delta v in order to turn, right? So the square root function kind of helped with that. So there's obviously a lot of sort of crafting that goes on here, right? Do what I want, but don't do it in this way. And okay, you can be a little bit You can degrade delta V when delta V is high. There's all this sort of tinkering that's going on. One of the open challenges in evolutionary robotics. We can't just say, evolve the best thing and get back something that we find satisfactory. Yes?
So how did they discretize that? Was that fee calculated every single, like every tenth of a second or however quickly they could?
Yes.
But did they look at fitness over the entire run as well?
That's a good question. So for every tick here, this corresponds to one recording of the 10 values and computation of phi, and then they integrate or sum up phi over all of these ticks. So I should have probably put that in the slide here, but this should really probably be phi sub t. So it's the value of fitness at a given point in time t, and then we're going to sum up all the phi t's to give us one final phi. How well did it do at v and delta v and I as it was racing around the track, or colliding with the wall, or not moving, or spinning, or whatever it was that it was doing? Yeah, that's right. Or moving side to side, whatever it does. That's right. Okay, so this one's kind of hard to read, but it's basically sort of showing you where each point here corresponds to one controller, how evolution is trading off these three terms. It's hard to see in this picture, but generally the points are rising in height, which is 1 minus I here, and V and so on. So this is, again, evolution moving through the space of, moving through a space. This is not the fitness landscape. This is fitness space, right? This is how it's improving these three terms or trading them off as it goes. Usually our fitness function has more than 3 terms, so we usually can't make this picture because the picture would be in more than 3 dimensions. But again, for this simple experiment, it's nice to sort of have all these different views onto exactly what evolution was doing in this simple case. Okay. They took their robot like this, and they set the evolved solution aside for a moment, and they put in the Bratenberg vehicle. So you can see the width of these lines corresponds to the weight now. The wider the line, the greater the magnitude. In some cases it's negative, in some cases it's positive. So they're basically building a Bratenberg coward by hand. And you can see here, like the original Bratenberg, it's perfectly bilaterally symmetric. The left side of this robot looks exactly the same as the right side of the robot. But there's a problem with that, and they visualize it in the top left there. So they took the Bratenberg vehicle, they pointed the Kepler into the corner, and what happens?
Can't figure out how to turn away.
Right, it gets stuck, right? So it goes into the corner, and maybe there's a very slight difference. There's a little bit more light on the left, so it turns away. Now there's a little bit more light on the right, turns back. And you can sort of see it jittering and coming to a stop in the corner, right? The coward is cornered. It can't get out of there. They did exactly the same thing. They took the Kepler back and put it in exactly the same place that the Bratenberg vehicle started, and it didn't get trapped. Why not? This is visualizing the synaptic weights for the Bratenberg vehicle. What do you think the pattern of synaptic weights is in the best evolved individual?
Asymmetric.
Whatever it is, it's asymmetric, right? So the investigators forced symmetry in terms of excitation and inhibition, but the amount of excitation or the amount of inhibition, evolution came up with a asymmetric solution, which again is great because it gets you out of corners. Again, humans tend not to think that way, right? We like nice, clean, symmetric things. Evolution says, no, asymmetry works. It's harder if I asked you to sit down and make a program the weights of this, but you can't use bilateral symmetry because that gets you stuck. It's harder to do, which is just yet one more example that evolution often comes up with a solution that works perfectly fine, but is sort of non-intuitive for us. Yes?
Does that mean then, like, this particular evolved individual would be pretty much only good at counterclockwise tracks and
Absolutely.
clockwise ones?
Exactly. So it does perfectly well. It actually does better than a Bratenberg vehicle on its home track, But if we were to take it out and put it in a different track, probably not so much, right? Which again is one of the open problems in evolutionary robotics that we'll talk about in a couple weeks' time. How do we get our robot to generalize? It would be nice to evolve it in one maze, or maybe 2 different mazes, so that we could then take our evolved robot and put it in any other arbitrary maze, and it might not do optimal, but it would do good enough, right? How can we ensure that that's going to happen? Nobody knows yet. That's a big open problem. Okay, as was mentioned a few slides back, the actual top speed of this robot is 80 millimeters per second. If you build a top speed Brakenberg vehicle and ensure that it never lines up with one of the corners, it'll do pretty well. Why did evolution never come up with that solution? The evolved solution travels at a maximum of 48 millimeters per second.
Is there a problem with local optima? Like, would it get to a point where it felt like it was doing well enough and then not continue trying to improve?
That's absolutely a possibility, right? So in this case, we don't even know that 80 is, well, we know the top speed is 80 millimeters per second, right? So maybe that's the global optimum, and it never got there. It's 48. There might have been, in the space of all possible neural networks, given these constraints, something that did, but they never saw it. And what they argued in the paper was not necessarily that it was stuck on a local optima, but it had to do with the speed, the refresh rate of the sensors. So a robot that's traveling at 80 millimeters per second takes a snapshot of all of its 8 proximity sensors, moves 80 millimeters per second, and at the next update of the sensors, it's already crashed. So who knows what that refresh rate is? Doesn't matter. Evolution says I can really only travel at 48 millimeters per second given the slow refresh rate of my early 90s sensor technology here. So it might have been local optima, and we could test that if we took a Kepler today and replaced these sensors with modern day sensors that refresh much faster. And now we might see that the robot can evolve a faster solution. Or not. Maybe the evolutionary algorithm still gets stuck in local optima. So the reason I bring this up is, again, evolution is saying, I can't do everything. I have to evolve a solution that works with the limitations of my own body and my environment and so on. And we often don't know a priori what those are. Again, that's sort of a non-obvious thing to do. If you're trying to write a controller for this robot by hand, how fast should you make it go, right? Hard to say. Okay, so that was arguably the first evolutionary robotics experiment. At about the same time, there was a second experiment going on in the UK using this very odd-looking robot, now known as the Gantry robot, developed at the University of Sussex. Seems like a Rube Goldberg device. Got a lot of these crazy moving pieces. Obviously, one piece that's the same here is they're going to do all the evolution on an off-board computer, and the computer is connected with the tether to the Gantry robot. What is the Gantry robot? It sits on top of a table, and the actual tabletop has been cut out. And then you have this trolley, which in this picture is the X trolley, the big trolley, where we can send motor commands to that trolley. Positive means move to the right side of the table. Negative values mean roll towards the left side of the table. So we've got a trolley moving along the top of this table. And then on top of the trolley is another trolley, smaller one, that's traveling in the Y direction. Send a motor value to the smaller trolley, and it will move backwards along the big trolley or forwards along the big trolley. So, like the robot we just saw, 2 motor neurons, 2 motors. One motor allows travel this way, and the other motor allows travel this way. Seems odd, right? Okay, it's going to get even more odd. Hanging down through the center of the smaller trolley is an inverted periscope that you see here. So we have a camera that's actually pointing down. That's the camera housing here. And the camera is pointing down, and it's pointed at a small dental mirror that's angled at 45 degrees. This is why it's the periscope. And the dental mirror can rotate around its long axis. So the camera is pointing down, but because of the mirror going at 45 degrees, it can see off to the side, and as the dental mirror turns, the robot can sort of see all 360 degrees around itself. So 2 trolleys with an inverted periscope speared through the center of it. Very, very odd. Okay. So in this case, this robot actually has 3 different motors. One controls the big trolley, the second controls the small trolley, and the third controls the rotation of the dental mirror, which is basically where the robot is looking. So the robot itself, you can think of it as the dental mirror. That's the thing that's actually traveling around under the table, and we can put lots of little things, obstacles on the floor, and have the robot try and avoid them, and so on. Why the heck would you make such a strange contraption?
Well, like now you have something that can move like anywhere in the XY plane. Like think about like moving packages or like kind of like an arm to get things from point A to point B.
Possibly. We can't lift, the robot can't lift anything up, right? So it can't really move around, grab something and move. It's still moving through the XY plane. It cannot move through the Z plane. But so can the Kepler. It can also move anywhere it wants around the table. Why go to all this effort? Why not just use a Kepler and have done with it, be on the table?
Couldn't you just say that they just wanted to see what would happen?
Yes, that often happens in science. Let's just see what happens. Remember, this is early 90s technology, so this is a really painful thing to set up. They had a pretty good reason for doing this.
I guess maybe there's just like less that can go wrong if the 2 things are on a track.
Yeah, less things can go wrong. Remember the Kepler, right? We had this little thing driving around a table. It took them almost 3 days to do this. What were they actually doing during those 3 days? Remember, they have to evaluate, or the computer has to evaluate one controller after another. I don't know how big the population size was, but there was probably thousands or maybe tens of thousands of neural networks they had to try out on the Kepler. It was probably a poor grad student. It's always the grad student that gets the grunt work. The grad student had to go in at the end of each evaluation, every attempt around the track, take the robot and put it back where it started, right? Because we want to try and level the playing field. Every neural network we're going to try out on the robot, we want to make sure that neural network is starting with the same initial conditions as the neural network we just tried. So there was someone over those 3-day period that would take the Kepler wherever it ended up and put it back. What about the Gantry robot?
Just go X, Y, Z rotation and you're done.
You're done, right? So you can press a button and the whole thing will go back to its initial condition. It might hit some of these objects on the way back to resetting, and they probably had a way to get around that. But they were automating this whole process, right? They're limping along at this point because there's no simulation technology, and they're just trying to automate this whole process. So without touching the system can evaluate one neural network after another on its own. That's the reason for all the intricate mechanical engineering here. Okay. So let's keep going. We know what this robot looks like. What about the sensors? We know the motors, the 3 motors. So underneath the dental mirror was this little plastic circle, and the circle was bigger than the radius of the turret. So as it was moving around under the table, that plastic circle might bump up against something, and they had a little switch in there that they could detect the bump. And depending on how it fires, they could determine whether the robot was bumped from front right, back left, or front left. So they sort of, from that bump event, they created 4 separate sensors. And those sensors are binary. Was it, at the current time step, was it bumped front, right, or not? 0, 1, or 0. Okay, so we got 4 bump sensors. What did they do with the camera image that was coming back from the inverted camera? Again, they did something which at the beginning looks a little bit strange, but once you think about it, it starts to make sense. They took the raw CCD image, the raw pixel image, They transformed it a little bit into polar coordinates, so we have a circle. Okay, so this circle, if you were to look at this picture, would be a camera image that's distorted, that's showing a 360-degree view. They have all these pixels, colored pixels, in this raw video image. They subsampled that raw video image by dropping into the image 3 circles. Those circles could be placed at any position inside that raw footage. And the radius of the circle was also arbitrary. And they dropped that circle. They would take all the pixels inside that circle, throw away the color information, but just keep the grayscale, and return a value between, or integers here, between 0 and 15, where 0 is perfectly black and 15 is perfectly white. Okay. So they take this pixel matrix and they reduce it to what's known as receptive field. So you have the same thing in your visual system. There's part of your entire visual field that you're more receptive to. There's certain fields that you're more receptive. The fields are averaged to this brightness value, and then the position and radius of these three circles is evolved. So again, up till now, as we just saw in the previous experiment, the only thing evolution had control over was the weights of the synapses. Even in the second experiment now, we're already starting to allow evolution to have freer reign. So now it's going to evolve not just the synaptic weights, but it's also going to drop these circles into the visual field. Question?
I don't really understand the circles. What were they?
Okay, so the circles are basically, back in the early 90s, they would have all of this raw information. So they'd have maybe 100 by 100 pixels, so they have 10,000 pixels. And then for those 10,000 pixels, they'd have red, green, and blue 3 times. So they had 30,000 numbers that were flooding into the robot at every 10th of a second. They couldn't make a neural network that had 30,000 input neurons, right? It would just be way, way, way too big. So they said, listen, we're going to try and allow evolution to take those 30,000 numbers and then compress them down to actually just 3 numbers. So the input layer for this robot, the total number of sensors at the input layer are 7. 4 binary touch sensors and 3 numbers that represent something about the robot's visual input. So we're going to take the 30,000 and go to 3, and they're going to allow evolution to figure out how to do that. So inside every individual in the population, they're evolving a neural network, a set of synaptic weights, and in addition to the neural network, there are 9 additional numbers that evolution can also play with. There are 9 genes that are tacked on the end of all the evolved weights, and those 9 numbers are the x, y, and radius of the 3 circles. So 3 triplets. Make sense? So evolution, for any given neural network, it can decide where it wants to look and how much it wants to average over in that receptive field. So far, so good? Okay, so 7 incoming values and our 3 motor neurons that control the big gantry, small gantry, and the movement of the camera. Okay, so like we saw before, now that we have our robot, we have its sensors and motors and its neural network. We're going to connect those 7. Sensors up to the 3 motors. What do we want to get the robot to do? They did something a little ambitious here, which is ultimately in the 3rd experiment, they're going to start to do categorization. So now we're going to try, down here, we're going to try and evolve a robot that is afraid of squares and likes triangles. Okay, but before we did that, they sort of wanted to exercise their system. So this cube here represents the underneath the tabletop, right? So on the back side, between the 2 back table legs, they put up some Bristol board. And first, they just put up all black Bristol board. And they just wanted to evolve a robot that if they took that robot and they put it at 4 different initial positions, would always approach the big black rectangle at the back of the table. So they're going to now, unlike in the previous experiment, they're going to take each genome, which contains synaptic weights and those 3 receptive fields, and they're going to try it out 4 times on the robot, and the robot's going to start in 4 different positions. So they're going to want to see on average how well the robot does. What would you suggest for phi 1? We're going to try and construct a fitness function for this. Assume for the moment that we're just going to keep this pretty simple. We're just going to have the x and y coordinate of the robot at any given point in time. What would be a simple fitness function that would reward for always moving towards the back of the table? X is going to be to the left of the table, negative x to the left of the table, positive x to the right of the table. Negative y is to the front of the table, and positive y is towards the back of the table.
So you want to maximize y and you don't care about x.
Maximize y, right? Just go to the back of the table. That's good enough. Okay. I'll do the reveal when we go through the other 2 here. Okay, so maximize y in all 4 cases. That one's pretty easy. Okay. Now they're going to do another experiment where they're going to now place, again, each robot is going to be evaluated, each controller is going to be evaluated 4 times. For each one of these 4 trials, they're going to flip a coin. Heads, they're going to put the black Bristol board at the back right of the table. Tails, they're going to put the black rectangle at the back left of the table. So you're going to put the rectangle at different places. They're going to take the position of the Gantry robot at any given point in time, x and y, and they're also going to take the position of the black rectangle. So you have those 2 pieces of information. At every point in time, you know where the black rectangle is, and you also know the x and y of the robot. What's the fitness function now? We want, in all 4 cases, the robot to approach the black rectangle.
We want to maximize y and get x to the x coordinates of the square.
We could do that. So we could just say maximize y, always go to the back, and minimize the difference in x between the black rectangle and that. That will work in this condition, right? But it wouldn't work if we then took the Bristol board and put it on the front of the table, which they didn't do. Then you would change the fitness function.
I would just make it an absolute. Can you just make an absolute value then?
Absolute value of what?
The y.
You could make it an absolute value of the y. Oh, between the y of the robot and the y of the...
Yeah.
Yes, you could. That's right. That's one. Again, there's many different ways to solve this problem.
Minimize the Euclidean distance between.
You could take the x and y of the center of the square and take the x and y of the robot and try and minimize the Euclidean distance between the 2. Go to the rectangle. That's pretty straightforward, right? No problem. These are just kind of sanity checks to make sure everything's working. I don't know if they reported in the paper exactly what they used, but it was probably something like these. Okay. Now, you're going to evaluate the robot again 4 times. These are only just 2 pictures. Oh, I'm sorry, I drew this wrong. There were 4 cases, but I'm only showing 2 and showing the initial position and then sort of desired final position. Okay, so in these 2 evaluations here, if these were the 2 starting positions, we want the robot to go to the triangle. So again, in the 4 evaluations, heads, rectangle here, triangle here, tails, rectangle here, triangle here. What's the fitness function now? We want to go to the rectangle but avoid triangles as much as possible.
Do they have to, can we, at this point, understand, through pixel data, what a triangle is?
What is a triangle? We're going to come to that in the next slide. That's a really good question. Assume, again, for our purposes, you just have the position of the turret, the position of the center of the rectangle, and the position of the center of the triangle. That's what we're going to use to compute the fitness of the robot. But remember, the robot itself has these receptive fields, so it can see its environment, right? So let's focus on the fitness function first. What would we need to do here?
So it seems like the Euclidean distance is now better.
Euclidean distance between the turret and
The triangle.
rectangle, right? We want to minimize the Euclidean distance. We wanted to, oh, I'm sorry, you're right. We just switched to triangles, thank you. Minimize Euclidean distance to the triangle because this robot loves triangles. And maximize distance from the rectangle. Okay, so that's just the intuition. You can copy this down, or better yet, you can try and figure this out yourself. It's not too hard, right? We have the y components and the x coordinates, and then I'm just putting in d here a short form for the Euclidean distance between something and something else. So as you're writing this down, these you can probably do. I would focus on this one for a moment. So let's have a look here. We're summing, in all cases, from 1 to 4. So remember, we want to see the average ability over all 4 cases. We're not strictly taking the average. We're just summing. We don't even bother dividing by 4. Why not? Being kind of lazy here. Why are we not dividing by 4, or the number of trials?
Consistent across.
It's consistent. Remember, we're always just looking for relative fitness. Things that have lower fitness are going to die off, and things that have higher fitness are going to survive and reproduce. So it doesn't matter whether it's the overall sum or the mean. They're all getting the same treatment, so it doesn't matter. So you'll see some of this mathematical laziness as we go along. Doesn't really matter, right? As long as we're treating everybody the same. Okay, so what's going on down here? We can see that in each of the 4 cases, we have a difference term. So in this case, we're trying to maximize the distance of the rectangle from the robot itself. So stay as far away from the rectangle as possible. And we're going to penalize you, minus, for any distance between you, the robot, and the triangle. So minimize distance to the triangle and maximize distance from the rectangle. They had to put alpha and b in here to sort of tune these weights a little bit because the robot was, it was a little bit jerky, and there were some other reasons for it. Doesn't matter for our purposes, but this might be useful for you later if you want to reward something very strongly but provide a mild penalty for something else. You can have a big alpha and a small beta. So you can reward and punish for different things and tune how much or how strongly you reward and punish different things. So far, so good? Okay. So we will, actually good timing today, we will finish with, and again, if you didn't get all this down, it's all being recorded in the video. You can get the rest after the fact. Okay. Let's finish today by looking at a single evolved controller. This was the best one that they got. Let's start at the top. If you look carefully, you'll notice that there are 4 trajectories here. Each one of these little moving pieces, the circle represents where the turret is, and the tail represents where the turret just came from. Right? So we can see sort of over the entire trajectory where the robot was going and sort of how it was turning and going towards the rectangle. What can you tell me about its movement pattern?
It's looking at its surroundings and then moving.
It's looking at its surroundings and moving. How do you know that?
You can see it's making circles and then finishing the circle with a direction.
That's it. Now remember that there is also the turret itself that's spinning, so it didn't necessarily have to do this corkscrew motion. It doesn't have to actually move in a corkscrew to see. It can stay perfectly still. It can move neither of the trolleys, but spin the dental mirror. So this is kind of odd. Why the corkscrew motion?
Is it looking in the pixel data for like vertice, say?
Possibly. Yep.
It doesn't have the ability to see different levels of light or brightness.
Maybe. So this experiment is from 1994, so how old does that make it? 23 years? We're still not sure. It's all of the above. And this often happens with these evolved solutions. They're hard to understand, but your intuitions are right. There's whatever it is, it's looking for something. Now what it's looking for is hard to say.
Is it like the problem of like flat land, we don't know that that's a triangle, and you have to move closer to see, oh, that square is always like this, but if I move the triangle, it's gonna like do that. The sphere goes through the plane.
So you were asking, how does it see the triangle?
Well, it's like the classification or segmentation issue, isn't it? So then like,
It has to move. It has motion sort of through the dental mirror, but that's just sort of giving it a 360 of its field of view. But when it moves, everything around it moves relative to it, right? So it probably is the case that these big corkscrew motions, at least for 3 out of the 4 trajectories, helps it, right? By moving itself, everything else moves. And when I'm moving, all of your heads relative to the other heads are moving, right? So I'm getting a lot of information the moment I start moving, right? I can sort of figure out who everyone is more or less if I stay still, but it's easier if I move, right?
do they use movement to form depth perception when not using stereoscopic vision?
They could, but there is no depth here, right? There's just a two-dimensional triangle, a two-dimensional rectangle, so you don't need depth information.
If you have the center of the triangle in the center of the rectangle, then when it moves, you can tell that it's gotten further from one of them and closer to the other.
You're getting closer, right? So as it moves, sort of the relationship between things changes, but this relationship is much more subtle than I got further away from the triangle and closer to the rectangle, because we don't even know that this robot can see the triangle or rectangle yet. What does the triangle mean to the robot? We've taken all the actual raw pixel values and thrown them away, right? So just, yes?
I mean, the main difference that it's going to see when it's looking at them is it's going to see brighter at the top and not as bright at the bottom for the triangle.
Now we're getting
The square is
closer.
going to be
Right.
full, so it's going to be trying to maximize brightness at the top while also minimizing brightness at the bottom of its field.
You're getting closer, right? So there's something about darker at the top and lighter at the bottom because it's this inverted triangle. Yep.
So when it gets closer to the square, the number's going to be like high the whole time. Say, or then like if it gets closer to the triangle, it'll be closer to the middle because there's going to be some light and some dark.
Getting very close now. So let's look at let's open up the robot and see what's going on inside. First thing I'm going to show you is here's our input layer here, and here's our output layer here. We've got left motor, right motor, and the spinning of the dental mirror. So we've turned the neural network on its side, output layer here, input layer here. Remember that the robot had 7 sensors, but it turns out that this particular controller basically doesn't use the other 5. They're either not wired up with the weights, or the weights are very, very close to 0. The evolution basically said, I don't need those other 5. All I need is V1 and V2. Which are 2 of the 3 receptive fields. So the third one, it's in there, but it never influences the motors. So they stripped away in this picture everything except those things that affect the movement of the 3 motors. So we have V1 and V2. V1 is here and V2 is here. And just to make this a little bit clearer, this circle here represents the robot looking horizontally, right, as the dental mirror is moving. So we have one visual field that's up and to the left and the other visual field that's up and to the right. How is it using that to recognize triangles and rectangles? Remember that it's also moving, right, about its environment. What happens as it's moving and hits the side, let's say the right side of the rectangle? What happens to these 2 visual fields? It's looking to the right of the rectangle. It doesn't even see them. What are the values of those 2 receptive fields? Light or dark?
Light.
They're both light, right? It's looking at some light background. It starts moving to the left. What happens when it hits the rectangle? One sensor goes dark. The top left one goes dark, and it keeps moving, and the bottom right one goes dark. Right? Okay. Now let's imagine it's looking between the triangle and the rectangle and also turns to the left. Same thing happens. Top one goes dark and then the bottom one goes dark. How can it tell the difference between these two objects? There's one subtle difference between those two situations.
If you're in a square, then you could say like the time between sensor 1 and sensor 2 changing.
The time between the two of them going dark is different for these two objects. And last observation for today, look at the synapses here. Some of them are connected up here, and some of them actually go backwards, go around, and then go forward again. These are recurrent synapses. What do recurrent synapses give you? Memory. Recurrent synapses give you memory. So if you have memory, you can remember when the top left one went dark. And if in your memory, the timing of those two things is different, and you tend to turn at the same rate in all cases, you can tell the difference between a triangle and a rectangle. So I'm going to say triangle and rectangle. I'm going to finish today by saying triangle and rectangle in scare quotes, because this robot's understanding of a triangle and a rectangle is very, very different from ours, but it can still tell the difference between the two. Think about that, and we'll come back to it on Thursday. Thank you.